Since we started these videos on Introduction to Statistics, we've been talking about how we really want to explain what's happening in the greater population, but because of time or cost or because the tests are destructive, we really can't gather information about everybody in that greater group, that greater population. So instead we take a sample, a subset, and then we analyze that subset, that data, and try to extrapolate or draw inference around the greater population. So really we're estimating, we're guessing. And according to a Chinese proverb, to guess is cheap, to guess wrongly is expensive. So we want to make estimates, we want to make statements about the greater population, we want them to be accurate as possible. And so really what we're trying to get to is being able to model, to represent how much uncertainty there is in that estimate. And so throughout our videos, we have looked at how you can get more precise estimates about the population. A random or probability sample will get you there. A larger sample size will get you closer there. Now we're going to start talking about different statistical inference methods to get to that estimate. So statistical inference is the process of making judgments about a population based on properties of that sample. And we want that sample to be randomly drawn from the population, so a probability sample, if at all possible, because then we can be confident that our sample has the variability and is similar to what's in the population. So then we can analyze that sample and make statements about the greater population. Now, how do you make judgments about the population? Well, one option is to estimate. We can have a point estimate. We're approximating the value of some unknown population parameter. So we've been talking about sampling distributions and using the sample mean and the distribution of the sample means through repeated sampling to get to a population parameter like the population mean or average. So we're trying to get an estimate of that value. We have a point estimate and we have a confidence interval. A confidence interval is a range of values for that unknown parameter. And we want to look at how confident are we in order for that it's with that parameter, that unknown parameter is within that range. And so we can be more confident, but then it's harder to detect. We need bigger sample sizes. So there is a trade-off, right, in terms of that level of confidence, being able to detect, and how big of a sample size that we have. The other way we can draw statistical inference is to do hypothesis testing. And the part that you can't see behind my head says that it involves choosing between two opposite statements concerning a parameter. So we might be looking at that we think the proportion who vote Republican is greater than 55%. And so the alternative there would be less than, or the null hypothesis is that it is, we could do equals 55% and then the alternative is not equals, or we could have the null hypothesis be greater than or equal to, and then the alternative be less than. Your equals is always going to be in the null hypothesis. So we're going to need to talk about what we mean by null hypothesis and alternative hypothesis, which we're going to do a couple videos from now. These videos we're going to focus on first are going to be about that point estimate and confidence intervals. So estimation has many practical applications. A business analyst might want to determine the expected profit from a particular investment. A physician might want to estimate the average waiting time for his or her patients. When we talk about a point estimate is a single statistic used to estimate a population parameter. So essentially with a point estimate, we're saying this sample average is what we're using to predict the population average, a single statistic, as opposed to confidence intervals, which uses the sampling distribution and the multiple samples. So we have multiple sample statistics to get a range of values. Okay, so we expect the point estimate to be close to the population parameter, but remember, it may not be exactly the same because as we have seen, as we've taken the average, for example, of our families and the different number of children they have, each time we took a different sample, we got a different sample statistic. And recall, the difference between a sample statistic and a population parameter is what we call sampling error. Okay, the difference between the sample statistic and a population parameter is what we call sampling error. So a point estimate, using it to say what's happening in the population, is going to be off a bit by the amount of that sampling error. So examples of point estimates we've talked about already. We have the sample mean. We talked about how we use the symbol x bar. It's a point estimate for the population mean. We use the Greek symbol mu. The sample proportion, p hat, is a point estimate for the population proportion, p. We can also look at point estimates for standard deviation. So the sample standard deviation S is a point estimate for the population standard deviation using the Greek symbol sigma. Okay. And so we've actually looked at all these before. We've talked about some of these symbols. Variance, remember variance is standard deviation squared. So sigma squared is the population parameter. S squared is the sample statistic. We're going to talk in a later video about correlation. And so for correlation, we can also do a sample statistic to look at the relationship of two variables within the sample, and we represent that with an R. And if we're looking at the relationship between those two variables in the greater population, we use the Greek symbol rho, which looks a little like a P. All right, so suppose, just to clarify here, I used to teach stats at Baylor University in Texas, and so that's why these examples from my slides here are often used Baylor students as an example. So just if you're wondering why it keeps appearing. And the colors are green and gold. And if you look at some of my other videos, like the ones with research design and business intelligence and analytics, teaching for Red Deer Polytechnic, and so I think those slides match their colors instead. So that's why you see different slides. Different institutions where I've taught these different courses. All right, so suppose I ask 100 randomly selected Baylor students how much money they spend on textbooks purchased for this semester. The sample average for 100 students is 382.25. This example is from 15 years ago, back when books were way cheaper. When one book, or all your books were 382.25, now one book is 382.25. Although if you buy my book, it's not 382.25. All right, so suppose the average for 100 students, their books for the semester is 382.25. So suppose I make the claim that Baylor students, all Baylor students, spend an average of 382.25 on textbook purchases in this semester. So I'm taking my sample of 100 students and I am doing a point estimate to say, okay, that sample statistic, that average of 382.25, I am then going to infer that the average for the entire population, all Baylor students, not just my 100 students, that the average they spend is 382.25. So our X bar here is 382.25, and I'm using a point estimate to talk about the population mean, mu. Is that true? Is the average amount that all the students spend on textbooks in that semester, is that 382.5? Well, if in fact the number is not 382.5, let's say it's 400, then our sampling error is going to be that 382.25 minus 400, and we can get that difference, that sampling error. Well, it's quite possible also that we could take a different sample of a different 100 students and get a different number. And that is where we talk about the fact that our sample statistics are random variables. They do change. And so that's why we'll ultimately get to the idea of a confidence interval, a bit more of a range, to represent the fact that that point estimate has sampling error, and we want to consider that the sample statistic changes from sample to sample. So we can never say with absolute certainty what that population mean is. In order to have absolute certainty about what the average that all Baylor students pay on textbooks, we would have to do a census and poll every single student. And again, we may not be able to do that because of cost, because of time, because the test itself, in this case, it's not, because we would just be surveying. But sometimes the tests are destructive, and so you wouldn't want to eliminate all the students. Okay. So we are going to talk about confidence intervals shortly, which allows us to improve beyond the point estimate. But just to wrap up the discussion about point estimates, let's look at this example here. A manufacturer of batteries for portable hand tools wishes to investigate the length of time a battery will last. A sample of 12 batteries has a mean length of time of 4.3 hours. We know the standard deviation of battery life is 0.3 hours for the population. So first, why are we sampling in this case? Well, in order to test the battery life, we have to use it up. And so the test here is destructive. So it doesn't make sense to do this for every single battery. We would have no batteries left to sell. So we take a sample of 12. Now that sample of 12, so n equals 12, has a mean length of time of 4.3 hours. So our point estimate here, and here we're dealing with means, so x bar is equal to 4.3 hours. And we are then going to use that x bar to say that the population mean mu is 4.3. If all batteries last an average of 4 hours, what is the sampling error? The difference between our sample average and our population mean is 0.3 hours. So we have a sampling error for this particular sample of 0.3 hours. Okay, so recognize that we could take one single sample statistic and infer about the population. But the risk there, of course, is that it is going to have sampling error because each sample is a different group of items within the population. And so there's going to be some variability of that. You can increase the likelihood that your point estimate is accurate if, one, you have a representative sample. So you choose randomly from the population. So we randomly choose the batteries, not just choose the first 12 that we produce or the last 12 we produce, but we randomly choose throughout the production process. And the other thing is to make sure we have a big enough sample size in order to represent the variability that exists within the population. Both of those techniques are going to reduce your sampling error and increase the accuracy of your point estimate. In our next video, what we're going to do is look at confidence intervals, a range of estimates that's going to take into consideration that sampling distribution.